the study area, looking to the west. Here's the Aleutian Trench. Here's the Surveyor fan. Here's our mountain range. The way you do this is pretty simple. It's conservation of mass. You just have to fill out all your boxes. So the first box that I'll work you through is the flux coming in. This is the tectonic flux. So that YAKUTAY block, here's the front of that subduction zone going offshore. You've got that coming in. You've got to figure out what's going out. There's a flux out of the mountain range. And then the flux out, of course, because we're looking at this over millions of years, we have to account for any mass that got lost through subduction or accretion. So we have to account for this flux in here. Lots of little boxes. And I think one of the things that we've learned is how to really, another take-home message is how to deal with uncertainty in all these measurements. And I'll work you through those as well. So just to kind of show you what goes into building the model, here is our flux in. What we need to know is the width of the block that's accreting, as well as how fast it's moving. So that's based on modern GPS measurements. And we have a lot of evidence to suggest it hasn't changed much in about 6 million years or 8 million years. So we have a length and a uncertainty and where the edge of that is, as well as a velocity and uncertainty there too. What we need now is the thickness. That comes from seismic refraction data that was done where they look at the crustal thickness off there. And from that you can see that it's basically in an order of about 4 or 5 kilometers thick that's coming in. So we have an uncertainty there too of about 1 kilometer. So between the uncertainty of that and the rate and the width, we can come up with an uncertainty in the volume. So how much mass is entering the system over millions of years. So that's our influx. Then we need to figure out what is leaving. And so my colleague Sean Gulick and his students have spent a lot of time looking at seismic reflection data to look at the volume of material that's out in the deep sea. And the one reason we have success in this area is that there's a tremendous amount of seismic reflection data collected mostly by the USGS back in the 80s. And we've been able to reprocess that data using new data that we've collected to help us reinterpret the old data. So because the USGS and the Gloria program went back and forth collecting single channel seismic on all these areas, we have basically what's called a isopack. And what's important, this is thickness, but it's a thickness in time, because that's what seismic measures. So one of our big things that we have to figure out is to convert from two-way travel time to a volume in rock. Well, we noticed, and this was Sean's student Bobby, that there are basically two main sequences, seismic sequences that he could map around. Sequence 2 is an older one and 3 is the younger one. And so these colors here show it's thicker. And so we've got more mass, theoretically, in this interval here than this one. And this is what we were drilling through to calibrate. So we need to know the area. So our uncertainty also includes estimates of uncertainty on the total boundary here of the fan. This is the Surveyor fan. It's one of the largest fans on the planet, certainly one of the thickest. And then this is the kind of data that we get from the drilling program that allows us to do this, the budget. And so we drilled out here to about 740 meters depth. This is the seismic profile that Sean had collected before. This is again in two-way travel time. We have to use the drilling to tie what we see in terms of our physical properties in with the seismic data. And so from this we get density, because we need porosity for all of this. We have to account for the volume that is made up of pore space and what's the volume of solid rock, because we're doing everything in terms of volumes of solid rock. We get that from the drilling. We also then from the drilling get estimates of seismic velocity, because then we can take it from two-way travel time to an actual thickness. And so we have, here's our seismic sequence 3 boundary and our 2 boundary in here. And we have uncertainty as to how thick that is based on the thickness of the wavelet, which is the sound pulse that's going out. So, and then there's uncertainty on the, you can see there's a lot of scatter here in the porosity data, and there's uncertainty in the velocity models that we're using. So this is kind of how we come up with turn that seismic volume into a thickness. The other thing we need to account for is the amount of mass that has been lost over this time period. So we use that seismic isopack and 3 transects along here to average out a thickness of material that's going into the trench. We multiply that by the velocity, and so we come up with the amount of mass that we've lost from the system. So we can account for what's going into the mountain, coming out of the mountain, and then going into the trench, and we're losing it. So if we tie that all together, theoretically, we can do this big test. Of course, we need age control. And so shipboard age control, if you go out to sea, is primarily done with two techniques, biostratigraphy and paleomag stratigraphy, which I'll show you both here. So what we were able to do is recover back to about 10 million years into the Miocene. In the North Pacific, we have a lot of biosiliceous microfossils. They turned out to be useful, but we also actually had incredible preservation of calcareous microfossils. Even nanofossils in some intervals, but also foraminifera. And if you know your North Pacific geochemistry, the CCD is really high there. But we still were able to preserve all the way back to 1 million years. There was 800 meters depth, pretty clean forams that we can develop oxygen isotopic stratigraphy. And that's probably reflecting the fact that the stuff is buried really quickly in clay-rich glacial rock flour. So it gets out of that zone and gets buried. So we were able to use diatoms primarily, but also rads and foraminifera for one of our age models. Post-cruise, we've been able to work, Alan Mix and his group have been able to do oxygen isotopic stratigraphy on some of the shallow sites that we drilled. So 1419 is up on the slope. We got back about 60 million years. The depth was about 200 meters below the seafloor, all piston cord. And so we can come up with an age model for here. Since then, Mo Davies, who sailed with us, she's been able to develop a pretty good radiocarbon age model for here. So we've got that. And then we also had the PMAG, which Joe Stoner was our PMAG person out there. And it turned out to be one of the more phenomenal records that's ever been observed in terms of paleomag. You know, the basics idea, you know, you have reversal stratigraphy here. And, you know, the reversals are well dated onshore. But the thing is, it's the depths at which these are occurring. For example, at 1417, we've got the Bruns Mariama at about 130 meters, and we've got some other ones in here. At 1418, that first transition, which is about 700,000 years ago, is at 650 meters below the seafloor. So the SED rates here are just phenomenal. And the preservation of this is incredible. What was sort of sad for poor Joe was that we had great recovery. Where we're drilling and we're bringing back big cylinders of rock. And we only lost one interval. And it's the one interval right there, right during the transition. And it would have been the highest resolution record of the Bruns Mariama transition ever. And Joe wants us to go back and re-drill that. So, but I said, well, we got you this transition. Isn't that good enough? And he's like, no. So you can never keep the PMAGs happy. So anyway, we've got this great age model from Paleomag, and they're refining it with more data post-cruise. All right, so the results. What do we find? All right, so we have a transect I'm going to show you here. It goes from 1417 all the way onshore. And what we found is a major climate change going from the Pliocene into the Pleistocene. Kind of what we expected, but it was a pretty interesting record out here at 1417. We have SED rates that are actually pretty high, but you know, out here we're 500 kilometers from the mountain range. The transition out here, and I'll show you some pictures, went from a very interesting clastic type of environment of major landslides in through the Pliocene, where we know it's warm in that area. The sediments themselves are just as green as you could get. There's no ice or rafted debris in it. The productivity appeared to be pretty high during that time period, which is an interesting case because that's where we're headed to climate-wise. So if the past is any key to the present, the future is going to be warm and productive in the Gulf of Alaska if it follows the same kind of weather patterns. Climate patterns, at least. So that's the Pliocene. And then right here, we saw this major transition into glacial material and another transition right about 1 million years ago. So we were able to tie those all in with our shipboard data. Because the key here, I should point out, with the Paleomag, this transition right here is right at the end of the mid-Pleistocene transition. So we have this like golden spike in our cores we can look at. So what does it look like? These are the cores. So this is what the North Pacific looked like in the late Miocene. It's alternating between this green and brown, bioturbated. So the color in here, we haven't worked it out, but it's some probably Milankovitch periodicity to it with the global climate in the Miocene. Here's what the Pliocene looks like. Like I said, it's all green. What's interesting about the Miocene also is it alternated between this sort of variable productivity, but then also these deposits. They're diamix, but the name. So it just means that they're large clasts surrounded by a muddy matrix. Some diamix are created by ice rafting, other diamix or glacial material. Other diamix are created by landslides. And this is a case of landslides because these clasts are actually made up of the seafloor itself. But at the same interval we have these. We also have these types of diamix, which are made up of little clasts of wood and coal. And we have a piece of wood that was carried all the way from onshore. It still has the bark on it. And there's coal fragments from onshore coal fields. This is 500 kilometers out to sea. So again, in the Miocene, it's even further out away from. So in the Miocene, there were time periods where the whole continental margin was just failing as massive landslides and just running out in the Gulf of Alaska. And it kept occurring again and again and again. There's a whole lot of missing rock onshore that has coal in it in some formations. We think a lot of it's been moved offshore. And we think it's related to big-scale tectonic things that are happening. So there's a really great tectonic story in the Miocene. There's an interesting story to be had here in the Pliocene. But the big thing that we found was the transition into the Pleistocene. And these are our first intervals of ice-rafted debris. You can see that there are these little stones that are in here. But these all date to right about 2.6 million years ago, which is kind of what everybody thought was sort of when you would see development of ice sheets in the area. It also dates really closely to onshore records for the first ice sheets. So that, as opposed to the older data, which had ice-rafted debris earlier than this, we didn't find anything earlier than this. For us, it really is the Pleo-Pleistocene boundary. But after that, it's evidence of large-scale ice rafting out there. So that's when the glaciers and the ice sheets get turned on. But we also have these occasional time periods where it becomes incredibly productive. This is much closer to shore. Glaciers leave. They go up into the mountain range, and the ocean is free of ice, and what you end up with are these amazing laminated sediments. This has been pretty well known for the North Pacific during the last deglacial, but we've seen this several times in the late Pleistocene. So there's high productivity. We think it's tied into the delivery of iron through glacial runoff, and maybe through rock flour and things like that. Because this is an iron-limited ocean up there. And so by hitting it with that iron fertilizer, you get these major blooms of diatoms that settle out. And it also becomes, it's already low oxygen, becomes even more low oxygen. So this is kind of the take-home point here is that, yeah, right at about 1 million years ago, or 700,000 years ago, there's a transition, well, at 2.6, there's a transition into glacial material. But then at about 1 million years ago, we also see another transition into combination of ice-rafted debris, but also a lot of productivity. So the ice is becoming very dynamic. Another important thing is that we drilled up onto the shelf. Recovery was really rough here, but we drilled on the continental shelf 1 kilometer down and still did not reach the Bruns-Matayama boundary. So it's all younger than 700,000 years. Now, these are sed rates that are on the order of over 1.5 meters per year, and if you're to do this on kilometer scale, it's 130 centimeters per kiloyear. So these are pretty high rates of sed. And we also see really high rates up here on the slope as well. So lots and lots of sediment coming off of the mountains that's accumulating here on shore. The other thing, too, that I'll point out is that, I'll come back to this, the tectonics are also linked in here. Where you see the fastest moving ice, these big ice streams, are also where the rock is coming up the fastest. So the work they've done on shore, there's a link between where the ice is occurring and how fast the rock's coming up. But also, it's in a zone where the tectonics are the most active as well. So it's that chicken and egg kind of a thing. To link it back into sort of the global question in climate that we're looking at about the mid-Pleistocene transition, this is an example of one of the seismic reflection profiles coming off here that Bobby was able to map up. So this is an example of what these sequences look like. And this is kind of what we had before with age control. But the main thing is we thought it was in the Pliocene when we saw this transition. We now know that this is at the Pleo-Pleistocene boundary. These are new data that just show the stratigraphy of the fan out here. So that lower unit that's got all the mass transport deposits, it's this interval here, and then everything above it, you'll notice there's a channel right here. It gets turned on right at that point. This is really important. The SURVEYOR channel is the main distributary of stuff coming off the mountains. From the drilling, we now know that it dates to 2.6 million years. That channel did not exist before the glaciers were there. And so the glaciers were so important in terms of moving mass off the mountains that it set up this distributary system. So that allows us now to map this one interval we see here all the way around the fan and put an age on it. And so this is kind of what we've done. We've tied into our well here, but also at 1418. So we have two ties. They're the exact same age for this interval right here. And so 2.6 for this. Now we've got a volume per time that we can come up with. Some of the other interesting things with the stratigraphy, if you really are curious about long-term late Cenozoic climate in the North Pacific, this kind of summarizes a little bit what we're looking at. So the Miocene is kind of made up of that alternating sort of productivity and mass transport deposits. This kind of shows you here biosiliceous oozes. They become actually more common at the site from the early to mid-Pleistocene. And this is out in deep water too. So whether or not, we don't think this reflects necessarily change in preservation, but it might be related to the increased delivery of iron to the system. We also see lots of volcanic ash because you're near the Aleutians. So we have colleagues that are working up a record of changes in volcanism over millions of years in the area. Lots of gravity flow deposits. This is a submarine fan, so it's made of lots of turbidites here. But it's sort of this interesting transition that we have where we go from the onset of ice-rafted debris into the Pleistocene. So quite a lot of stuff for people to work on. So if we look at an interesting way of sort of evaluating this, goes back to the figure I showed you in the beginning. One of the records should be increase in SED accumulation rates if all of a sudden you're eroding more material off the mountains. And so these are our records for accumulation rates, sedimentation rates, binned here on 500,000 year intervals. This shows in red the oxygen isotopic record, and this is a running mean on top of it. And these are our SED rates. And what's kind of interesting, if you go back to that model that I showed you of ice sheet development in a glacial, and what was a fluvial range going through the 40 kiloyear to the 100, it predicted an initial slug of sediment coming out as the ice starts to erode. You begin to get glacial erosion, and then it drops off. And then it ramps back up again as the ice begins to move down valley. We've seen similar things out here in terms of it was relatively low, and then as soon as the ice forms, we see the step increase, and then it becomes really high, and then it drops off. And it's not until we hit that mid-Pleistocene transition do we then see the secondary pulse. So we would contend that this is one suggestion that we are seeing that response that occurs on shore, going from small ice sheets to big ice sheets. We also see at the same time, this is ice-rafted debris, so number of loanstones binned, is it drops off in that period and then it ramps back up again at the initial part of the mid-Pleistocene transition and then has dropped off since then. Could be either due to the fact that you don't get big ice coming in that area or the number of icebergs has dropped off in time. There's a problem with this approach though. Anybody ever heard of the Sadler effect? It's something that's been brought up through stratigraphy for quite a long time, and that's the idea that as you begin to integrate over longer time periods of the geologic record, you have a greater probability to lose time, either through erosion or non-deposition. So because of that, we would expect the most complete record for the most recent time, and then as you go back older in time, it should get less and less in terms of volume. You take that same thickness and divide it over time, you come up with lower SED rates. Also, too, because of the way that natural delivery systems work, is like a river system will avulse. So you could have a spot like on the Mississippi River Delta that has relatively high SED rates for a while, and then when the river avulses, high SED rates go over here, this drops off. So this sort of internal dynamics also can affect a point measurement in SED rate here. So the first time that we submitted this paper, one of the reviewers came back and said, well, you got to take into account the Sadler effect, which we thought we'd done, but we didn't do it well enough for the reviewer. And so in the revision, we specifically addressed it. And the best part of it was Sadler actually came out with a paper last year that said, if you do X, Y, and Z, you can overcome all of this. And the X, Y, and Z was you need to have a total volume of the system. You need to cover every last bit going in and out, which we've done. You can't use sed rates, and you need to have a time, you need to be away from the continental margin to be able to do this. You need to be out in sort of the deep sea. And we've covered all of those with our approach. So Bobby Reese had developed this cartoon of what's happening in the North Pacific over the Miocene, Pliocene, and Pleistocene. And this was based on the previous records. And so starting off a long time ago, this is right here, about 5 million years ago, this is when the fan, he thought, was just getting started. And actually now we know it's only at 2.6 million years. Before that, we had basically a large amount of delivery coming in from landslides and tectonic activity building up the mountain range. Then we see the onset, he said 5, now we know it's 2.5, of the first growth of ice and the delivery out and the formation of the fan. Keep in mind, too, that this is all rotating to the northwest through time because of the movement of the plate. And then we hit the mid-Pleistocene transition and the real large-scale development of the SURVEYOR fan. This is actually something we've confirmed with the drilling. So the mid-Pleistocene was a major change in the two there. And then where we are now. And so this is sort of the current state. And what we were missing in the model was the tectonics. All right, here's the answer. What we've done is the flux in and flux out. We've summed up all of the things and applied a Monte Carlo approach to dealing with all the uncertainty. So we ran 1 million simulations, varying all of those parameters. And then what you see here is the result. And green is for sequence 2, so 2.6 to 1 million. Blue is 1 million to the present, or 1.2 to the present. The difference in the offset has to do with the thickness of the colliding block. If it's 4 kilometers, you get the, oops, sorry. If you get 4 kilometers, you get this one. If it's 5 kilometers, you get this one. So you see the difference between the two. We also did it, so I did the Monte Carlo. Alan Mix did a, oops, sorry, wrong button. Did a just propagation of uncertainty using Excel. And so he did the same thing where he took all of the unknowns, took the uncertainty and ran it through a model and came up with the same kind of probability distribution here. So here he's looking at the difference between pre and post and also comes up with a difference. So both approaches, we have a 97% probability that there is a net difference in the volume flux between the two time periods. So that there was more mass coming in. And in fact, if you look at it, what's interesting, and we'll go back to this one. So here is the difference. Influx minus efflux. So in the Pleistocene to the mid-Pleistocene, there was actually more mass coming into the mountains than leaving it, which under the models would suggest that the mountains got bigger. Then, about 1 million years ago, 1.2, the whole system became negative. And so given our uncertainty here, we think that we can show that the system has switched from net accumulating to net eroding. And so it should have a feedback then on the tectonics. So one of the interesting things about this is that for the paper, the revised paper, we put in the Python code to do the uncertainty modeling. We had this Excel program for any of the reviewers to put their own values in. And all of the tabs in the Excel